Hello and welcome to the Build at Scale lab at Purdue University. Today, as part of our integration guide series, we will be learning how to integrate an MSI AMR which runs REST. This is the MSI AMR that we will be integrating today. It has a Techman TM12 ARM mounted on top of it to form Rosie, the autonomous machine tending cobot. Stay tuned till the end of the video for an additional Sparkplug implementation of this. Now, let's take a look at the documentation.
This is the user manual for the MSI AMR, and it gives us all the information we need to use the Fleet Management System, or FMS in short, to control the robot. This is the FMS used to communicate with the AMR. It shows the current map the AMR is on, along with various points of interest. This button here starts the mission manager and enables commands to reach the robot. One thing to note regarding the mission manager is that you only needed to be in the start condition for sending commands, but not for receiving telemetry data such as battery level, error state, or even positional data. This allows us to pull information from the robot even when the mission manager is not in the play state. The panel on the side gives us information about the AMR, such as its current mission, the robot state, the map information, and even a battery level indicator. As I mentioned earlier, this AMR uses REST for its external communications, and the user manual has a pretty good explanation of how this works and which endpoints we need to hit. A basic understanding of REST APIs will definitely help here. In this video, we are going to go over the following concepts: polling AMR state information, sending missions to the AMR, polling ongoing mission information, finding out the state of the mission manager on the FMS, finding out the connection state of the AMR for Wi Fi disconnects, and a complete integration loop where we use all the concepts we have learned together to form a complete loop. All the code we use in this video will be available in the GitHub link in the description. There is a lot of useful AMR state information we would like to pull from the robot, such as which map the AMR is on, what its battery level is at, whether it is charging, the mission status, positional data, and so on. A lot of this information can be obtained from this endpoint right here, the getAGV endpoint. We will use this post method with the payload that is shown here. The option will be filled with name because we are just pulling information from the one AMR. The AGV name will be MSI underscore 56, which is the name of our AMR. The response will be in the format specified here, with an array of information which is shown here. To access the information, we will need to access the specific index of this array in the response. Please note that the index of this array starts from 0. Now let's take a look at how to put this into practice on Node-RED. We use Node-RED to handle integration due to its simple visual UI, but please note that you may use any language of your choice. Since we're dealing with REST APIs, I am going to use the HTTP request node to handle the communication. The endpoint we want to hit will go into the URL section over here. For the payload of the message, we can use an inject node. This node will trigger the message along with the payload of our choice. A debug node will help us catch the response. Now, let's test this out. First, let's take a look at the HTTP request node. The method we have to use is a post method. And for the URL, let's take a look at the user manual. Here, they have given a URL, and in this section, we have to fill in the IP that has been assigned to the AMR. So let's try first copying this and putting it into this URL section. Now in this section, we just have to put in the URL. So this is the IP of our FMS, and that's what we will be pinging to get our information. Now that we're done with that, let's look at the inject node. In the inject node, we do not require a message topic, so let's take that out. Now, for the payload, we would like to send a JSON string. Now let's expand this. To know what exactly goes in the payload, let us take a look at the user manual once again. Here, it has given us an example for the payload. First, let us take a copy of that. Let's first paste the payload. And in the section of option, we are going to fill name. And in the section AGV name, we will fill MSI underscore 56, which is the name of the AMR. Now let's try connecting all of them. And let's hit the deploy button to save our changes. Now let's test this out. When you hit this inject button, it sends a message to the HTTP request node and gets us a response from the AMR. If you look in this panel here, you will see the response that we have received from the robot. To make this a little more easily readable, let's add a JSON conversion node over here. This will help convert this output from a string into a readable JSON string. Let's save. And now let's re-inject. This is the new response that we have received from the AMR. And as you can see, it is in the form of an object instead of a string. Now expanding this, we can see all the information that we have received from the AMR. We have received information such as the map, the battery level, and even the mission status. Sometimes, not all of this information will be useful for you, and you might prefer just taking certain parts of this information. To do that, we can use a function node to extract specific information. A function node will let us write our own code to extract information from this response. For example, say you want to extract the current map that the AMR is on. For that, let us first copy this path. And now in the function node, we need to create a new message.payload. We will open a JSON object here. And we shall create a new key called map. For its value, we will give it the path that we have copied earlier. This is the path that directs to the map output in the response that we receive. Now, let's test it out. Let's hit the inject button once more. And as you can see, the new output gives us only the map. This is how you could extract specific information from the response for use in your controls logic. You could even do multiple different sections at the same time. For example, you may want to also extract the battery level. That is in space number 5. Don't forget to add the comma in the previous one. Make that change and try hitting the inject once more. So now your JSON object is updated and also showcases the battery level. So this is how you make use of the getAGV endpoint to collect specific information from the AMR. Sending missions to the AMR is done through the setMission endpoint. The payload body for this method is given here in the manual. There is also further elaboration about the individual parts in the following table. The most important section is the task array section. This consists of mission steps which are executed sequentially. Each mission step has its own format and they have all been described in this manual. For this example, say we want the AMR to first go to the point RA office, then to the VLM, and finally back to dock. All this must be captured in the task array of our payload. Similar to the previous example, we shall once again use a HTTP request node, but this time the endpoint shall be set mission. As for the payload, since it is a little more complex, we shall use a function node to set it up. For the payload structure, let's take a look at the user manual. This is the payload structure. As you can see, it has a start time, a using time, user ID, a robot type, a robot mode, a robot name, and finally the task array. I have a pre-made version of this so that we can save some time. This is the pre-made task payload code that I had written down. One thing to note is that the start time needs to be in seconds and hence converted. The remaining sections are fairly self-explanatory. For the task array, we can go back to the user manual to get a better idea. The first two steps are going to be move two steps, and this is the task array structure we need to follow. So let us copy this over first. Here you may note that the first section is the point where we want to move to, and the second section is the map where the point exists on. Let me illustrate this with an example. So in our case, this is what the move to step would look like. We want the AMR to go to the VLM, and that VLM is on the map Lambertus 1263. So let us replicate this for the first step. Here the only change is that the VLM now becomes the RA office. Now let's move to the third step, the docking step. Back to the user manual. Here we can see that the dock to step is very similar to the move to step. The only difference is that the point is replaced with the dock name. Now let's go back to Node-RED and set this up. Here we change the move to a dock to. And instead of the VLM, we input the name of the dock. This should now accomplish what we have set out to do. Now that we're done with the payload, let's include an inject step. Note that we do not require either a topic or a payload in this case. Next, we can include a debug step to capture the response. And let's also throw in a JSON conversion node to convert the output into a readable format. Now, let's just connect all our nodes and deploy to save our changes. Let's try running this flow and see how it works. Remember that the set mission step will only work if the fleet management system or the FMS is in the start state. Let's try running the flow while the FMS is in the stop state. You can see the response in the panel here, and the result is fail. And the value, which is the reason for the failure, is that the mission manager is stopped. This is an expected result. Now, let us try changing the mission manager to the start state. Let us try rerunning the flow. Now, as you can see, the result is success and the value, which is 20, is the mission ID. This is how we use the set mission endpoint to send commands to the AMR. To poll ongoing mission information, we can use the get mission endpoint. This endpoint can tell us information about both finished and unfinished missions in the current instance of the FMS. This can be differentiated in the payload we send with the HTTP post method. In our example, we will use the category unfinished to get data from the ongoing mission. A task ID of -1 will return all ongoing mission information, both queued and running. If there are no ongoing missions, then it will just return an empty array. You can use this information to handle specific conditions in your controls logic. Using the same IP and port as before, we just have to change the endpoint to get mission. As for the payload body, we can find that information in the user manual. This is the message payload that we need. Now, let's just copy it over to our flow and put it in an inject node. We'll put it inside the message payload and change it to a JSON format. Now, let's add the usual JSON conversion node as well as a debug node to print the response. We should also include a function node so that we can check the response payload and find out whether it's empty or not. This will tell us whether there is an ongoing mission. But before that, let's test out the flow and see what the output looks like when there is no ongoing mission. Let's deploy to save changes and test out the inject. As you can see, the result is a success. However, the finish and the unfinished missions are a null payload. This implies that there is no ongoing mission. The finish being empty implies that no missions have completed in the current instance. Instead of printing out the whole response body when there is no ongoing mission, let's change the payload to a simple phrase to represent that. First, let's copy the path of this unfinished payload. Now in the function node, let us check if that unfinished payload is empty or not. This is where we would copy the path. And here, let us add an index for checking. We want to check if this is a null. So let's add the word null here. And if this condition is true, we change the payload to something very simple. No ongoing mission. Let's click done and deploy it. Let us try this new flow. Now we have fixed the output. Let's try running the same flow when there is an ongoing mission. The AMR has begun moving on its mission, and now let's try re-injecting the flow. Now, since there is an ongoing mission, the value of unfinished is not empty, and instead gives us an array with a whole host of different attributes. You may use any one of these in your controls logic. To find out what each of them mean, we can visit the user manual once again. This table over here tells you a description of what each and every field means. And that's how you use the get mission endpoint in your controls loop. Earlier, I had mentioned that the AMR can only take commands when the mission manager is in the play mode. This section is going to cover how we can pull that state information for use in our controls loop. For example, you may even want to check the state of the mission manager before attempting your machine tending loop. Please note that the following steps are very specific to this particular situation. So let me start off by saying that the regular API does not have an endpoint which can give us this information, at least not directly. After a lot of fiddling around with the various endpoints, we find our answer. When you attempt to send a mission to the AMR while the mission manager is in the stopped state, it sends us a failure response in the error text. Turns out that this is the only way we can obtain information about the state of the mission manager. Now that we know this, we just have to refine it for use. However, sending an actual command every time we want to know the state of the mission manager seems pretty pointless. Therefore, we can just send an empty task array in our mission payload to prevent this. This is the same setup that we used in the set mission payload section. In this function node, you can see that I have deleted all the extra steps, and now the task array is functionally empty. Now, let us try injecting this flow to see how it works. Note that the mission manager is currently in the stopped state. The response tells us that the mission manager is stopped. Now, let me change the mission manager back to start mode. Let me try re-injecting the message. And now it tells us that the task array is empty, which implies that the mission manager is not stopped. This is how we use the set mission endpoint to figure out whether the fleet management system or the FMS is in the start or in the stop phase. Sometimes you may encounter this Wi-Fi disconnect error on the FMS, which prevents the AMR from receiving commands. In my case, this was happening very frequently, and it became apparent to me that I needed to include a tag which could capture this state information. The issue with this was that that information could not be captured using any of the REST endpoints available in the manual. It wasn't even available as a response. So I had to do some digging around the script window running in the background until, lo and behold, there was a custom endpoint right here. This could ping the AMR directly instead of through the FMS. I immediately put this to use and figured out that not being able to get a response from this endpoint is indicative of a Wi Fi disconnect problem. Now, let's see how we can put this to use in Node-RED. The endpoint we will use is getMISC, but the IP now will change to the IP of the AMR directly instead of the IP of the FMS, which exists on a laptop. Getting a response from this endpoint would directly imply that there is a connection established with the robot. On the other hand, not getting a response or catching an error from the HTTP node implies that there is a connection error. Now, let's build out the rest of this flow. First, we need an inject node. We also need a JSON conversion node, a function node to change the payload, and finally a debug node to catch the response. The inject node will contain the payload for this HTTP request. The payload for this endpoint is the MAC ID of the AMR. I have saved this information in a pre-made inject node. This inject node contains the payload body that we need. So let's replace this older inject node with this new one. Let us test this flow out without adding anything in the function block. Now let's inject. As you can see, there is a whole host of information that you receive from this endpoint. But the main takeaway is that you receive the information. And this receipt implies that there is a connection established with the AMR. Now, we don't really need all of this information. We just really want to know if the AMR is connected or not. So let's add some changes to the function block. Instead of the message payload being the whole body of the message, we can replace it with a simple phrase such as AMR online. Now that we've done that, we've finished with the function node. Let's try injecting once more, but don't forget to deploy before that. Okay, let's inject. As you can see, instead of the whole body of the message, we just receive a simple phrase, AMR online. Now it's time for us to test it out in the disconnected state. I have induced a Wi-Fi disconnect error in the FMS as shown. Now let me try injecting this flow. As you can see, the HTTP request node is currently requesting information. After about 10 seconds of request, it has sent a message saying no response from server. However, you may note that the function node has not really done anything in this. So this is not the right way to catch this response for use in our controls logic. All we need to do is to catch the error that's coming from the HTTP request node. We can use the catch error node for this. Inside the node, let's change it to a selected node. And let's choose the get misc HTTP request node. Now let's use a function block to change the payload and a debug node to print it. Inside the function node, let's have it print out a simple phrase such as AMR offline. That should be good. Now let's connect all of our nodes and save it. Now let's try injecting the connection check one more time. As you can see, now we have received the AMR offline response from debug 77, and we can use this in our controls logic. And that's how we use this endpoint to find out the connection state of the AMR. In this section, I'm going to show you a couple extra endpoints that are really useful and will come in handy for the complete integration loop coming up. These are the pause mission, resume mission, and the cancel current mission endpoints. The pause and the resume mission endpoints are nearly identical and share the same payload body. This is what the HTTP request nodes for each of these cases look like. This is the pause mission by robot endpoint, and this is the resume mission by robot endpoint. The payload bodies for each of these endpoints can be found in the user manual. To save us some time, I've created these flows with the payloads and the HTTP request nodes ahead of time. The cancel mission endpoint is a little bit more complicated than the other two. This is because, as of this recording, the cancel mission by robot endpoint does not work. Instead, we need to use the cancel mission endpoint to cancel the mission based on its ID. To get the mission ID of the ongoing mission, we can use a response from the get mission endpoint. This function block here extracts a mission ID from that response and then inserts it into the payload for the cancel mission by robot endpoint. This payload is then sent with the post method directly to the cancel mission endpoint in the HTTP request node and then cancels the ongoing mission. Now, let's test this out. I'm going to begin a mission for the MSI AMR. This mission has a mission ID of 1. As you can see, the robot has begun the mission. Let us first attempt to pause the mission. Let's click on the inject for the pause mission payload. As you can see in the FMS, the mission has been paused. We also get the feedback from this pane over here. Now, let's use the resume mission flow to continue the mission. As you can see, that is also a success, and in the FMS, the mission has resumed. Now, finally, let us test out the cancel ongoing mission endpoint. Let's hit this inject node. As you can see, we have a success And in the FMS, the mission with ID number 1 has been cancelled. So this is how you use the pause, resume, and cancel current mission endpoints. Now, let's make a complete integration loop. First, we would like to check the battery level, the mission manager state, and the connection with the AMR. After we have checked that information, we would like to send our mission to the FMS. We would also like to have a pause, resume, and cancel mission functionality. Once we have sent the mission to the FMS, we would like to check if the mission has begun and is currently running. And then we would like to check whether the mission has ended. And finally, we would like to loop back to the beginning and run it all over again. This is the complete integration loop. Now, let's see how we can build this in Node-RED. This is going to be our starting point. We have all the flows that we have learned about so far in this video. Now, let's begin with the initialization checks before sending our mission to the FMS. All of this can be accomplished with these three flows right here. First off, let's start off with checking whether the AMR is connected or not. Let's move these two out of the way. And in this flow, let's remove this inject node and add a new one which says loop start. We do not need any body. This will be the starting point of our loop. If you remember the earlier section, the output of this is either AMR online or AMR offline. Let's decide what to do in each case using a switch node. We can delete the debug nodes in this case and connect up the switch node. Here, let us catch two conditions: AMR offline and AMR online in the first and second space. In case the AMR is offline, we would like to send a error message. Let's say message.payload could be AMR offline, retrying after 10 seconds. And then let's print that. And that will come out of the first section. To retry after 10 seconds, let's add a delay node. Let's change the timer to 10 seconds. Now, let's connect a link out so that we can link back to the beginning. And let's link these two up. It just helps keeps the flow a little less messy. Now that we're finished with that, let's check the second step, which is the mission manager status. Once again, we may delete the inject node, and instead the second output of the switch comes into this empty task array. If you look at the debug node, you can see that the output of the response is stored in payload.value. Let's copy that. We do not need the debug node anymore. And instead, let's use a switch node to catch the output. Let's add our two scenarios. The two possible outputs for this flow is either mission manager is stopped or task array is empty. So let's add those two over here. Remember that it has to match up exactly with the response to be caught by the switch node. Mission manager is stopped. And task array empty. Once you're done with that, let's add a way to display error information. The payload could be mission manager stopped. Please start the mission manager and retry. And let's print it out with a debug node. Let's hook up the flow to the switch. We can deploy and simply test this out. The flow seems to be working. Next, let's obtain the battery level information from the robot. Let's use the getAGV endpoint to accomplish this. Let's transfer the information from the inject node into a function node. This is the payload of the endpoint. And now let's connect the second output of the switch node into this function block. Let's name it getAGV payload. Okay, now let's modify this robot info payload. Here we have a lot of information. We only require the battery level. To make things easier, let's first store the battery level inside a variable. Then let's use an if condition to check whether the battery level is above a threshold. Say 50%. We can set the message payload to battery level as battery and status as OK. Else we can make the message payload say not OK. We can delete this debug node and use a switch to catch these two outputs. We're going to check the message.payload.status with a capital S. And the two conditions are either not OK or OK. Let's connect these. In the case of not OK, we would like to send out some error information. We can simply say battery level not above threshold. And let's print it out with a debug node. Next, we can finally get into using the set mission payload to send our mission. Now let's grab the set mission flow from up here and delete this inject node. We can simply drag the connection from the second output of the switch straight to the set mission payload. We can also delete this debug node. Next, we need to figure out whether the mission has started. The get mission endpoint will come in handy for this. So let's copy that over. And for its payload, let's use a function block. The payload is present inside this inject block. So let's copy that over. It needs to be within the message.payload. That should be good. Looking at the FMS, we know that the machine usually has a tiny bit of delay before starting. To account for this, let's use a delay block with a small amount of delay. Around 2 seconds should work. Let's connect all these nodes. Let's also add a JSON conversion node to make the output a little bit more readable. Essentially, this will ping this endpoint every 2 seconds to get the ongoing mission information. Now, after this, we need to add a function node to check whether this is a null or not. And based on that information, we can tell if there is an ongoing mission or not. To test this, we can use the same if condition that we use in the get mission section of this video. And if it's null, we'll set the payload to not started. Let's copy that. And in the else, we can simply set it to started. Now we can use a switch to check for these two cases and make our decision. The switch will have two conditions. One will be the not started, and the other will be the started. Let's just connect these up. Now, in case the mission has not started, we would like to go back, delay for 2 seconds, and recheck to see if the mission has started before moving on. Let's also connect the previous JSON node to this delay. We can group all of these together to form a function. And let's just name it mission start check. Now this is the function that will help us check if the mission has started or not. This next part is fairly easy. We need to check if the mission has ended or not. The function that we made earlier with a little bit of tweaking can accomplish this. So let's just copy this over. These nodes can stay the same. The first change would happen in this function node. A null payload now implies that the mission has run to its completion. So let's change this message payload to mission end. And the else condition can be running. Now let's update this switch node to reflect this. Running and mission end. Let's change the name of the function. Mission end check. And let's connect this old switch block to this delay. We're now at the end of the loop. Let's add a function block to print out a small message and a debug to print it. The function could just say loop complete, re-attempting loop. Let's connect this switch to this function. And let's have a link out node to connect back to the start. This will help complete the loop. Now all that's left is to test this out. But before that, let's add a debug node here to know when the mission has started. One more thing I'd like to add is a loop counter, a way to know which loop you're running right now. For this, let me introduce to you a new concept. Let's start off at the very beginning with the function block. Here, let's add something called a flow variable. So flow variables are variables that can be kept track of throughout the flow. So let's initialize the variable flow.set. The name should be loop count. And let's initially set it to 1. So every time you hit the loop start button, your loop count variable gets set to 1. Now at the very end, we need to print that in our message and also increment it by 1. For this, we need to first get that variable. So let's have let loop count be equal to flow.get. We need to name the variable loop count. So now we've stored that flow variable inside this loop count variable. And in the message payload, let's just include that. So now it should say loop, the number of the loop, and then complete along with reattempting loop. Next, let's increment this. And finally, let's reset the variable. And its value is going to be the new loop count that we have incremented. Forgot to add a plus over here. So using all of this, we should be able to increment the loop and also print it out. Let's deploy to save changes. Now let's try testing it out by hitting the start button. As you can see, the mission manager is stopped and hence we have received this error message. Let me go change that. Let's try again. We have received the started message, and as you can see, the mission has begun in the FMS. As you can see, loop 1 has completed and it has reattempted the loop. The Wi-Fi disconnect also works since it says AMR offline, retrying after 10 seconds. And now the loop has restarted. Finally, I'd like to go through a Sparkplug implementation of REST to publish AMR state information as tags and their use in Ignition. Sparkplug is a software specification that builds upon the MQTT messaging protocol and is widely used in IIoT applications. If you're unfamiliar with Sparkplug and want to learn more, there's a link in the description to some content that describes Sparkplug pretty well. I have divided this up into two main sections: getting telemetry data out of the AMR and sending controls into the AMR. The node which publishes all the tags is this blue Sparkplug node shown here. We use this open source node palette here for this. We also need a broker setup which serves as a central source of all information. We can subscribe to certain topics on this broker and access the relevant information. This is the name of a broker and it has TLS encryption enabled for security. Here, you can set up the topic structure you want to follow for the information published. I have chosen build at scale as the group ID and robots as the node ID. The device ID has been set up as MSI AMR. In the first section, you can see some familiar flows such as the get mission, get AGV, and others. Using the Sparkplug B spec, I have set up different metrics which pull various data points of interest from the AMR at an interval of once every 0.1 seconds. For example, from the get AGV endpoint, I am publishing all the information in the format specified by the spec in this function node over here. Each metric has three main parts: a name for the metric, a value, and its timestamp. All the metrics need to be grouped together under the metrics subsection inside the message payload. A cool functionality of Sparkplug is its ability to track births and deaths, which basically is when the device or node goes online or offline from the network. Currently, the Sparkplug node does not inherently handle deaths, So I've set up this little section over here to handle device deaths. The watchdog timer keeps an eye on the responses from our different endpoints, and if we haven't received a response in the last 5 seconds, it publishes a death for that device. The HTTP error also checks for errors from the HTTP nodes and sends device deaths when it receives errors. An important advantage of Sparkplug is how lightweight it is, partly due to something called report by exception or RBE. Unfortunately, the Sparkplug node does not handle that inherently, so we had to come up with something for that too. This function node here gathers all the metrics and stores them as values. This array is then checked by this filter node based on the topic and only publishes a metric when there is a change in that metric. This helps bring down network latency considerably and gives us a good idea about how often our data actually changes. One final thing is the metric metadata. Each metric has a specific metadata packet attached to it that gets published along with the birth of the device. This contains information such as the data type, whether it is read-only, and even the engineering units. We need to push this metadata to the Sparkplug node before any of our other metrics get published as part of the spec. This is why the inject node for this happens a little bit earlier than the other inject nodes. This helps avoid race conditions. Next comes sending controls to the AMR. We do this using the DCMD or device command topic with the same metrics that we have set up in the telemetry section. The Sparkplug node sends the command out as a response, and we catch them using these link nodes over here. For example, take the current task metric we have over here. In the metadata, I have explicitly stated that this is not a read-only tag. This allows me to write to that tag from ignition and send commands to the AMR. I use the different keys in the payload to direct the commands to the correct endpoints. For example, a set mission payload will have a task array, while a get AGV payload will have the AGV name in its payload. This is what the tag structure looks like in Ignition. The group level is build at scale, followed by various different nodes. Inside the robots node, we found our device, which is the MSI AMR, and inside that, we find FMS with all the tags that are being published from the AMR through our nodered instance. The ones with lock icons next to them are read-only tags, and the other tags are the ones that we use to send controls. This cancel mission tag over here has been exclusively set up as a control tag to send commands. What you see here on the main area of the screen is a sequential function chart, or SFC. More specifically, it is an SFC which makes the AMR do a little demo loop running around the lab. This is what we mimicked in our previous section where we made a complete integration loop. This is a slightly more complex demo loop SFC which includes more assets such as the robot arm, CNC machines, and PLCs on top of the AMR. That's all we have about Ignition and Sparkplug for now.
I hope you found this video guide useful. Subscribe to this channel for more such videos. Thank you and see you next time.